Hello everyone. Today I'm going to talk about graphs. So what is a graph? A graph G as a pair of two non-empty sets V and E is defined like this. That each set, which we said that they are non-empty, it means that they should contain elements. V corresponds to vertices or nodes, and E corresponds to edges. And whenever the size of each set or both of them are infinite, then in that scenario we can call it an infinite graph. Otherwise, if we have a finite number of elements in each of these sets, then we can call it a finite graph. So this is how it looks like. It contains vertices, these points, as you can see, and they are connected by these edges. There are different types of graphs. So let's go through them one by one because it's important to distinguish between them. What do we mean by simple graph? It means that when you have two vertices, it's not possible to have a loop. So by loop, it means that this is an edge, and this vertex cannot be connected to itself by using this edge. And the other thing we could say about simple graphs is that it's not possible to have two different edges from one edge to another, one vertex to another. For example, if we consider this one as node A, node B, so it's not possible to have two different edges or more than one in general between these two specific vertices. So if we don't have such cases, then in that scenario we can call it a simple graph. Otherwise, if we have more than one edges connecting two specific vertices together, we call it multiple edges, and the graph itself is called a multigraph. And whenever we have loops, you can call them pseudograph. So this example is definitely a pseudograph, but even if it contains only one loop, it's good enough to say this is a pseudograph. And this example also is a multigraph because you see from Denver to Chicago, you can see that there are more than one edges. You see, from Denver to Chicago, more than two edges. We have another type of graph named directed. Directed graphs include arrows. So their edge is an arrow. You can show them like this or like this. Both of them are correct, but this one is preferred because when we are dealing with a complicated graph and we have so many arrows connecting to this one, so it could be a mess. That's why we usually prefer this one. So this example is definitely a directed graph. And what's the difference between undirected and directed graph? For example, between San Francisco to Denver, let's say it was an undirected edge. What would be the difference? Here it shows that it's possible to go to Denver from San Francisco, but it's not possible to go to San Francisco from Denver. But here in an undirected graph, if I denote this one by San Francisco and this one by Denver, it shows that they are connected. So it's possible to go from San Francisco to Denver or Denver to San Francisco. And based on the topic, sometimes these two graphs could be different in terms of meaning, because they are different because one of them is directed, the other one is undirected. But in terms of meaning, the way I define it for you, for example, you can go to Denver from San Francisco and vice versa. These two have exactly the same meaning. But based on the topics that we are talking about, sometimes it's important to use one instead of another. And that's why we need another type of graph named mixed graph. In mixed graph, we have both of them, both cases as directed and undirected one. Like, for example, let's say I have this and this. So what does it mean? It means that from A, you can go to B, and B and C are connected. So what does it mean? Based on the topic that we are talking about, it can get different meanings. And also, you can also show graphs like this. This one is not a mixed graph because all of the edges, there are arrows and they show that which direction you should go. But these graphs, they can have different meaning based on the way that you define them. And we need all of them. All of them can be useful, mixed graphs and undirected ones. Sometimes to use mixed graphs are more preferred because it's visually simpler. Like, let me give you this example. Like, you have again A, B, C. So you can go to B from A, and B and C are connected. You can go from B to C and vice versa. So these two, as I said, based on the way I define them, could have the same meaning. But if you have so many arrows between them and your graphs getting complicated, because this is a simple graph, as you can see, because usually graphs contain so many vertices and so many edges. So in that case, sometimes we prefer a mixed graph like this, so visually it's easier to show. Now we have a term, adjacent vertex. What do we mean by that? Two vertices U and V in an undirected graph G. We say this is an undirected. And later I will show you that what do we mean by that, because when we talk about adjacency matrix, it is both for undirected and directed ones. But when I talk about undirected graph in terms of adjacent vertices is only related to that. Otherwise, we should call it terminal. I will show you in an example. What do we mean by adjacent vertices anyway? They are called adjacent or neighbors in G if U and V are endpoints of an edge. So it means that 2 points or 2 nodes, 2 vertices which are connected to each other. These 2 vertices in an undirected graph, we can call them adjacent vertices. How can we represent them? Tables are very useful because we can summarize our graph into a table. That's the same reason we are summarizing our data in a statistic, because assume that you have millions of data and just with a simple table you can summarize everything. So this is the same case for graphs. It's very important to convert them. And later I'll show you how to convert them to matrices, because that's what we are going to do for lecture 12 at the end. This is actually the main goal of lecture 12. So assume that you have a simple graph like this. And here I want to have the adjacency list for that, as we can call this table. So first column belongs to vertices, the next one adjacent vertices, which belongs to undirected graphs. So what does it mean? It means that if I have a vertex A, it is connected to B, C, E. So B, C, E. This is true. For each of them, I can find an edge which connect them together. Like for example, B is only connected to A. This is true. So as you can see, tables can be very useful, especially when the graph is getting complicated, because this one is pretty simple. And this one is a directed graph example. From now, we should be careful about the differences between directed, undirected, simple, multigraphs, and so on. So here, even we can see loops, and this one is a pseudograph, and this one is also a multigraph. And we know this is directed one because E is connected to D, but D is not connected to E. Or better to say, you can go to D from E, but not vice versa. So here, instead of adjacency vertices, I use the term terminal. This is just related to notation. Otherwise, as you can see, for the list, still I call them adjacency list. And for matrices, for both directed and undirected one, we use adjacency matrix, which I will show you soon. So what does it mean? It means that A is connected to B, C, D, E, but this is a one direction. It means that from A, I go to B. From A, I go to C. And in case if there is a return, it should be specified in another row. For example, consider A and C. Again, from C, I should have A here, so that it shows that, yes, you can come back from C to A. So that's how it's done. And you see in front of this, it is empty. What does it mean? It means that there were some edges which were connected to D, but D is not going to anywhere. It means that I have such a case that here is D. Maybe some edges are connected to it. And from D, I can't go to any other vertices. So that's what it means. And here you can also confirm that from B you can go to D, from E you can go to D, but from D you cannot go anywhere else. So whenever you see such a case, that's what it means. And now it's a good time to talk about adjacency matrix. Now you know about the table version, but now we need to define them in matrices, because at the end we want to use them in our programming. We want to use them in our mathematical modeling. So we need to represent them as matrices at the end. Now here for the simple graph, this is a simple graph because it doesn't have any loop. For each vertices, we can say that they are connected not with more than one edge. So this is a simple graph. Whenever we are dealing with simple graph, we should know that the diagonal of the matrix should be all 0. You see? Because there's not a loop here. If this one was 1, it means that I had such a loop. And this is not directed, so I don't even show the direction here. So for a simple matrix, this is the case for sure. And another thing to notice is that these matrices should be symmetric. But first, before going through that, let me check with you whether you noticed. For example, A to B, this is 1. What does it mean? It means that A and B are connected here. You see? Let's call it, for example, E1. A, B are connected. That's why I show it by 1. This is an undirected graph. It means that if A is connected to B, so it means that B is connected to A. There's no advantage between any of these vertices. So it means that B is also connected to A. That's the reason this matrix should be symmetric. And whenever a matrix is symmetric, what does it mean? It means that the transpose of this matrix, if I call the matrix as A, then the transpose of this matrix should be exactly the same as the matrix itself. Why this is happening? Because I'm talking about an undirected graph, not just because this is simple. I'm talking about an undirected graph. And because of that, there's no difference between these two. And this is simple. So there's another thing I can say for simple graph when I take a look at this matrix. The other thing is that the values could be either 0 or 1. I cannot have 2, 3, and so on. What does it mean? It means that from A to B, I cannot have more than one edge like this. This is not a multigraph. So to sum up, I understand this matrix is a simple graph or representing a simple graph because the diagonal is all 0. This is not a pseudograph. It contains only 0 and 1, so it shows me this is a simple graph. This is symmetric, so most probably it should be an undirected graph. In a specific cases when we have, for example, for all of them going and returning with arrows, we will have still a symmetric matrix, but nobody uses that if we can just simply use an undirected graph. So another example, this one is a pseudograph. It means that for my diagonal, not necessarily all of them are 0, and there should be actually at least one of them as 1, at least one of them. If all of them are 0, this is not a pseudograph anymore. So here also, by having these values, I understand that this is not a simple graph because it should be multigraph. It has edges more than one between two specific vertices, like A and B. 3, you see, there are 3 edges between them. This is still symmetric. Why is that? Because this is not a directed graph. This is undirected graph. Okay, so I think you got the idea about adjacency matrices, but we have another representation of these graphs, and we call them incidence matrix, which is related to their edges instead of vertices, like this one. So what's the difference between this one and the previous one? In the previous one, as adjacency matrices, we had vertices for rows and at the same time for the columns. But here for the columns, we have edges. Okay, that's the difference. So the matrix you will have here will be different from adjacency matrix. And not necessarily the size of vertices is the same as size of edges. If I consider V1, V2 until V5 as elements of the set V, then what's the size of V? This is 5. What's the size of E if E1, E2 to E6 are inside the set E? Then we can call it 6. You see, these two are not necessarily equal. But whenever we talk about adjacency matrices, you see, we have a 4 by 4 matrix. Why is that? Because I'm using both the elements of the set V and V here for both row and column. These ones are vertices, the elements of my V in my graph. As you remember, for each graph, we define them as V and E. So again, to sum up, for adjacency, I consider only this set, but for incidence matrix, I consider both of them inside the matrix. That's how we represent them. So what does it mean? Like, for example, I have one here, another one here. It means that V1 and V4 are connected by E1. Is it true? Yes. V1 and V4 are connected through E1. So you see, for all of them, this is the same case. V1, V5 are connected through E2. V1 and V5 connected through E2. Yes, this is true. But you may ask me, what if we have more than 2 ones inside one column? What if we have only 1 instead of 2 ones inside one column? Let me show you one example. Like here, I have only a value of 1 here for my incident matrix inside this column. So column by column we are considering them, okay? So that we can draw the graph much easier. When it happens, it means that we have a loop. It means that V1 is connected to itself, not any other vertices. So here again, we don't have a loop. So E2 is not a loop. I understand it from here. E4 is not a loop. I look at here and say, yes, there are two ones here connecting V2 and V3. And here again, I have another loop, E8. You see? So it's very important to know how to convert a graph to matrix and matrix to a graph. This is what we are going to practice also in our weekly assignment. I think the idea is clear. You should only practice to know how it's happening. And you may ask me, what if here I have two ones? Is it possible to have another one here? I have three ones, for example. Is it possible? No, it's not possible, because the definition of the graph is that it is possible to have so many edges from one vertex to another, and we call them multigraph, as I said, but they should have different names, E1, E2, and so on. So it's not possible to say, okay, I have three different vertices, this is E1, all of them, this edge, I call it E1. This is not possible. That's why at most in each column, I should have two ones. Can it be all zero? If it is all zero, why do I need to define E5? So it's not happening also in incident matrices. Okay, guys, I think the idea is clear. We will practice it also in our weekly assignment. Please go through chapter 10, especially these two sections, and solve the questions inside 10.3. There are some examples with the solutions. Before checking the solutions, please go through them and try to solve them yourself. It will be such a good practice because your solution is in front of you whenever you want to check them. And again, we will check by a very useful weekly assignment, which contains converting graphs to matrices and matrices to graph. And we want to check them both for adjacency matrices and incidence matrices. Okay, guys, that was for today. And if you have any questions, please send me an email, or you can talk about it in our next online session.